Hello everyone, I'm Lou Del Monte and welcome to Del Monte on Science. This is part 2. We're discussing the universe's accelerated expansion. In part 1 I mentioned that the distant universes are moving away from us faster than the speed of light. Now, let's be clear on one thing. Einstein's special theory of relativity actually prohibits any mass, including a galaxy, moving faster than the speed of light, even at the speed of light. And yet we observe these galaxies moving away from us faster than the speed of light. What's actually occurring, the prevalent scientific opinion is that it's the space between the galaxies that's expanding faster than the speed of light. And there is no law of physics that prohibits that. And that gives us the appearance that the galaxies are moving away faster than the speed of light. So we have to actually talk about and discuss what is that space between galaxies. We know it's a vacuum, and we know it's filled with a lot of celestial objects, etc. But what is it that's making that space expand faster than the speed of light? Now, in my new book, Unraveling the Universe's Mysteries, available at Amazon online and available at Barnes & Noble online, I discuss the whole phenomena of virtual particles. That in a vacuum, and let's just take this to represent a vacuum, we see from various experiments, virtual particle pairs will actually come out of a vacuum. And this is pretty well established. There are a lot of experiments, the Casimir effect, the Lamb shift, a number of experiments describe this. And what we see are virtual particle pairs. We don't see them, but we infer their existence from the experiments that we've done. That one is matter, and I'm using a plus to represent matter, and the other is antimatter. These are virtual particle pairs, and they come out of a vacuum. And this is called a quantum fluctuation. It's a big term. And it's in accordance with the Heisenberg uncertainty principle. So let's describe, it's really the Heisenberg uncertainty principle that gives rise to this phenomena. So let's describe, what is the Heisenberg uncertainty principle? Well, what it says is that at the level of atoms and subatomic particles, everything is statistical. And so what that means is that the energy inside a vacuum is also statistical. And I'm going to draw a house. There's a house. And the house has 4 rooms. And when you heat the house, you try to heat it evenly, but you find out that if you had a very sensitive thermometer, the temperature here, T1, is different than the temperature here, and the temperature here, T3, T4. And that if you went around the various corners and what have you, you would not get an even distribution of temperature in the house. And that's the same thing about a vacuum. That's what the Heisenberg uncertainty principle is saying. It says that inside a vacuum, the energy in a vacuum, which we can't measure directly, is actually varying. And every so often it bunches up, using this to represent bunching up. And when it does that, it gives rise to these virtual particles. All right, I discussed that in fair detail in the book. Now, what this is asserting, because we can actually do experiments in laboratory vacuums, we're asserting that a vacuum has energy. And that's kind of a difficult concept, because we think of a vacuum as nothing, yet a vacuum has energy. And when we do experiments regarding a vacuum, we can actually demonstrate that there is energy inside the vacuum. And one of those experiments would be the Casimir effect, where 2 electrically neutral plates placed close together in a vacuum are pushed together. And I'll just give you a quick look at that. Here's 2 electrically neutral plates spaced very closely together, And when the virtual particles come out of the vacuum, there are more on the outside than can form on the inside because we have them very closely spaced together, so it pushes them together. That's called the Casimir-Poulter force. Now, this is taken, for the most part, as proof that vacuums contain energy. Now, you might say, okay, if there are virtual particles in a vacuum, and that's what I'm essentially asserting, virtual particle pairs, in order to maintain the conservation of energy. Most quantum physicists will agree that they're virtual particle pairs. Why is it we can't see these particles? And there's two reasons. One is that they may not actually be in the form of particles. They may be in the form of energy. And so we really can't measure energy. We don't have in physics an energy meter. Energy is an inferred concept, and it's measured in a context like chemical energy, thermal energy. And so if there is energy in the vacuum, we don't have an energy probe that we can put in there and say, this is what the energy of the vacuum is. The other is that if the particles themselves exist as particles in the vacuum, they could be so small that they're beyond our ability to detect. And how small is small? Well, they could be inside 1 Planck length. Now, what's a Planck length? A Planck length is the smallest distance in physics, the smallest measure in physics that we are able to theoretically postulate exists. Now, we're not able to measure a Planck length. We've gotten a Planck length is extremely small, and our capability is many orders of magnitude away from being able to measure that. We've been able to measure about 10 to the minus 18. Okay, and that's a 1 with a fraction of 1 divided by a 1 by 18 zeros after it. So it's a very small fraction. A Planck length is more in the order of 10 to the minus 37. I'm going by memory, so I might be a little off on this. But it's an extremely small measurement, and it's constructed, and I go through this in the book, it's constructed from the fundamental constants of the universe. So it's not arbitrary. We didn't come up with that. And that's why we may not be able to see it. So those are the two reasons why we're not seeing it. Now, in the next video, we're going to say, well, how does this explain why a vacuum is expanding? And we'll discuss that in our next video.